Do what I do. Most days. Just congrats you from mama's office.
You were grounding this morning for no reason. She woke up from a nap and started grounding.
I know. I didn't know what got into her. No, I did not.
So this is the stuff that will be on the file.
The first couple of questions will be on the fourth exam, and then the rest of it will be on the file. Oh, are you wrong? Are you wrong? Mama, not rotten. I'm not rotten, Mommy. Huh. So you think, huh? What the heck am I doing? 50147 out. Share. Where you going? Where do you think you're going? Luna. What do you think you're doing? You going visiting? She'll probably come to you. I'm gonna shut the door here in a few. No, Luna. Luna. She does. She just doesn't know she likes people. Have a seat and maybe she'll come to you. That's how it normally works best.
What's the best way to orient yourself in this classroom? Oh, screen's right there.
Yeah. No, where's my airdrop? I always forget how to airdrop. No. That's what I wanted. Yay, done. That way I don't have to do all of it from scratch. Go visiting. Chill out. Go visit. You can go visit. You can see my. Yeah. I'm not allowed to sit up here. If I wasn't there. Okay, let's go ahead and get started. First things first, your lab grade. You gotta sign in. Okay, so what we're going to be doing this afternoon is I'm going to do a couple more examples of interface formation, which is the last topic I was discussing this morning. My goal is to make sure that I do a reaction that isn't just a one-to-one reaction, so that we bring in that topic. Plus also I want to bring in one other concept associated with enthalpies of formation. That is the fact that when you're dealing with an element in its standard state, the enthalpy of formation is 0. So that is my plan with respect to enthalpies of formation. Then we're going to get into the gas laws, and don't worry about everything on the board just yet. It'll come when we get into the gas laws. Because what we're going to do is I've got a simulation that will allow us to explore gases. Since we're not in the laboratory, and hopefully get a better understanding of what the gases are really like. So that is the plan, and then we'll get into the mathematics associated with gas laws. So, and I'm going to go to this. Okay. So the very first thing we're going to do is we are going to calculate the enthalpy of reaction for 2 nitrogen monoxide gases reacting with O2 gas to form 2 nitrogen dioxide gas. Now, to do so, we are going to be using the enthalpies of formation under standard conditions for the nitrogen monoxide. That value gas, that value is 90.2 kilojoules per mole. And for nitrogen dioxide gas, that value is 33.2 kilojoules per mole. Now you may go, well, where is the oxygen in this with respect to these enthalpies of formation? And that is a note that I want to make sure you have. And that is elements in their standard state have an enthalpy of formation under standard conditions equal to 0 kilojoules per mole. So the reason I have not written oxygen up here is because that is an element in its standard state. Oxygen comes as a diatomic element and always in gas form. So it is in its standard state. So that means that the oxygen would have an enthalpy of formation equal to 0 kilojoules per mole. So if we want to calculate the enthalpy of reaction, that means we're going to be using the enthalpy of reaction under standard conditions is equal to the sum of the products of their number of moles times the enthalpy of formation for that substance minus the sum over the reactants of the number of moles times that enthalpy of formation. So our delta H of reaction would equal our products. We have 2 moles of NO2 at 33.2 kilojoules per mole minus, we have 2 moles of NO at 90.2 kilojoules per mole plus 1 mole of O2 times 0 kilojoules per mole. So when you key this into the calculator, you get a delta H reaction for this particular reaction equal to a negative 114 kilojoules. On the exam, you are given this formula, so you don't have to memorize it. And you are given a table that has the enthalpies of formation. Now, when you look at a table of enthalpies of formation, as I mentioned earlier today, you've got to make sure you not only look at the substance, but its state of matter as well. Make sure you pull the enthalpy of formation that is appropriate. Okay, so let's look at another example. Calculate the enthalpy of reaction for 2 HNO3 aqueous plus sodium carbonate solid goes to form 2 sodium nitrate aqueous plus H2O in liquid form plus CO2 gas. Given the enthalpy of formation under standard conditions for HNO3 liquid, which is negative 174.1 kilojoules per mole, HNO3 aqueous, which is negative 207.0 kilojoules per mole, Na2CO3 solid, which is a negative 1130.7 kilojoules per mole, NaNO3 aqueous at a negative 467 kilojoules per mole, water liquid at a negative 285.8 kilojoules per mole, and CO2 gas at a negative 393.5 kilojoules per mole. One thing that I have found useful for students over time, before you even do the math, so they don't accidentally grab the wrong enthalpy, I have seen students go in and go, okay, I have HNO3 aqueous, so they highlight the HNO3 aqueous. I have sodium carbonate, so they highlight the sodium carbonate. I have NaNO3 aqueous, I have H2O liquid, I have CO2 gas. In other words, if you've got a huge table, it's quicker to take that moment to highlight the ones that you have and then go in and do the math. That way you don't accidentally grab HNO3 liquid in this particular case. And make sure I grab the one I'm supposed to be grabbing. So our delta H of reaction. Now, I know this is going to be small. Apologize up front. I also know that I'm not going to put in all of the moles and the kilojoules and stuff like this because I only have so much space. So I have 2 of the NaNO3s times -467. I have 1 of the H2Os times -285.8. I have 1 of the CO2s times a -393.5. From that, I will subtract out 2 of the HNO3s times a -207 plus 1 of the Na2CO3 times, still ran out of room. Well, just so I can get it in here, times the -1130.7. When you key this into the calculator, you get a delta H of reaction equal to -680 or 68.6 kilojoules. So I'm always trying to give you hints as to things you can do to help ensure that hopefully you don't make as many mistakes. One of them was highlighting the actual components that you needed. The other thing that I find helps is for some students, they like to do this piece, get an answer, then do this piece, get an answer, and then do the subtraction. That way they don't accidentally forget to subtract out the -1130.7. So I find a lot of students will do just what's in brackets, and then do the subtraction. Questions? To me, enthalpies of formation are fairly easy as long as you can follow the formula. They're the easier of the math that we've been doing. Now we will get into gas laws. So what we're going to be doing, the first thing we're going to do today is we're going to basically gain an understanding of gas behavior. We will develop some gas laws based on the behavior. But as far as calculations are concerned, we'll wind up using the ideal gas law, a variation of the ideal gas law, that allows for calculation of density and molar mass of a gas. We will talk about the ideal gas law. With respect, or with stoichiometry involved. And then the last thing that we will do calculation-wise is we'll get into Dalton's law of partial pressures. So that's the plan for the gas laws. Now, to help us gain an understanding of the gas behavior, I'm actually going to show you a simulation, like I mentioned. That simulation hopefully will allow you to see many of the things about gases. For now, don't pay attention to what's on the board. Just focus on what's on the screen and we'll talk through a lot of it. Okay, so what I have here is we have a closed container that we're going to release some gas into. Now, there's two size particles of gas that I'll be working with. There's going to be a smaller version, which is red, and there's going to be a bigger version, which is purple. Now, as we do so, I'm going to play with some of the variables. Number one, I can play with how much gas is present. I can look at how that impacts pressure. I can play with the temperature of the gas and look at how that impacts pressure. And so we're going to just cause a simulation associated with our gases. So the very first thing I'm going to do is just release some gas into our container. And I want you to tell me what you observe initially. When I released gas, what did you observe? Okay. The particles move in a straight line until they collide with something. In many of the cases, it is bouncing off the wall, but it is also bouncing off of other molecules. What else did you notice when I started this process? Let me restart. And maybe I'll use the blue ones or the purple because they're a little bit easier to follow. What did you notice when I released the gas?
They were clustered.
It was clustered, and then what?
They spread out to fill the whole thing.
It spreads out to fill whatever volume is available to it. The volume of the gas is equivalent to the volume of the container it's in. Now, let's look at what happens when I add some red gas to this. What do you notice about the purple and red?
They're spread evenly throughout, pretty much. They're both taking up as much space as possible.
Correct. Both gases spread out to expand to fill the volume. The red fills the volume, the purple fills the volume. That's because gases mix thoroughly. As long as they're ideal, no reaction is going to occur, which is happening in this particular case. This concept here, folks, is something we're going to come back to when we get to Dalton's law of partial pressures. So we'll be back to that in a minute. But so thus far, gases fill the spread or spread to fill whatever container is available to them. Gases move in a straight line until they collide with a surface of an object. That object can be the container. That object can be another molecule. And what you will notice is that as the molecules collide, they do tend to slow down a little bit. I mean, that makes sense. What happens to you if you collide into somebody? You slow down too, because you give some of your energy to that other individual, and y'all both probably fall backwards some. So they collide. Gases mix completely with one another. Okay, let's start over. And let me put in, now I want you to watch the pressure. What happened to the pressure from the beginning? It's at 0. It's still at 0, 0. Oh, there's something. What happened? The collision causes pressure. So it's kind of like a balloon, folks, except I've got a hard container here. When the gas molecules are moving, they're moving rapidly, and when they collide with the surface, they're going to apply pressure to that surface. In the case of a balloon, when the gas molecules are moving around all over the place, they're bouncing off the inside walls of the balloon, and they're causing the balloon to be blown up because it's applying pressure to the balloon. Okay. Now I want to just restart this. I know I keep restarting. I'm going to try to only put in a few molecules this time instead of a bunch. Let it get all stabilized. What else do you notice about this gas now? Well, there definitely isn't. That's actually important. Well, that is one thing. I don't even have it up here. There isn't as much pressure because there's less gas. They're not any slower. They're moving about the same speed. What do you notice about the size of the purple dots compared to the black in the box?
It's less dense. There's less per space.
There is less per space, but let's just take, oh wait, I can pause this thing. Forget I can pause it. Let's just take these two. What do you notice about it? If you just look at these two dots and the space.
They're tiny.
They're tiny.
Like it compared to the whole container.
Gas molecules are tiny compared to the space between them. It's because gas molecules are so small compared to the space between them that we can actually condense gases. We have space that we can remove between our gas molecules, so we can condense gases because the space between them is much bigger than the actual gas itself. Now, if you're looking up here, we've used some words over and over and over again. We've used the word pressure. We've used the word amount of gas because we talked about, oh, there's more or there's less. We've talked about the volume. And there's one other component we didn't actually look at, and that was the temperature. In other words, there are 4 variables that are used to describe a gas. Those 4 variables are pressure, volume, temperature, and the amount of gas. Folks, this information really does go into the kinetic molecular theory. Kinetic molecular theory says that a gas is composed of molecules whose size is much smaller than the space between them. Gas molecules can move randomly at various speeds and in every possible direction. Except when a gas molecule collides, we don't have any attraction between our molecules. The number of molecules stayed the same. And when they did collide, those collisions were elastic. The only thing on the kinetic molecular theory we haven't gotten into is going to be the kinetic energy, which I'll show you now. Okay. Get my gas going again. So, you see how fast the molecules are moving around? Let's heat this puppy up. And what do you notice besides the lid blowing? What did you notice? Okay, they were moving faster and the pressure went up. One part of the kinetic molecular theory, well, the kinetic molecular theory says that the kinetic energy is related to 1/2 the mass times the speed. The speed is directly related to temperature because as I increase the temperature, the speed went up. Now let's look at how mass impacts it. And the speed. We put some purple in and we put some red in. Who moves faster? The red. The red moves faster because the smaller, meaning the least molar mass, the smaller the atoms, the faster the gas is going to move. Again, that comes back to the kinetic molecular theory. So there's 2 factors that impact the speed of a gas. which is kinetic molecular theory. Because remember, kinetic energy is the energy of motion. There's two factors that impact the energy of motion. The mass of the gas. The smaller the mass, the faster it moves. And the temperature of the gas. Because if you increase the temperature, you're going to increase the speed at which the gases move. It's still going to take the purple a lot longer to get up to speed than it will the red, because they are a bigger gas. And I blew the lid again. Okay. So again, that's kinetic molecular theory with respect to the gases. Now, we can talk about some of the gas laws that came to be. One of the gas laws is that the pressure of the gas is inversely proportional to the volume. To demonstrate that, let me recap this thing. I'm going to add red. Okay, check out the pressure. It's roughly 6 atmospheres. Now what I'm going to do is I'm going to increase the volume, and I want you to notice the pressure. When I increase the volume, what happened to the pressure? Decrease the pressure. Decrease the volume. Increase pressure. Increase volume. Decrease pressure. Means that the pressure is inversely proportional to volume while holding the temperature and the amount constant. Folks, that is the basis of Boyle's law, which is P1V1 equals P2V2. Now, Charles' law, unfortunately, I cannot really do here very well because we are talking about a rigid container. So I'm going to go to something maybe you have had experience with. You go buy a balloon. It's on a hot summer day. It's not today, it's on a hot summer day. And the party's still 4 hours away. So you got to leave the balloons out in the car. What's likely to happen to them? They're going to pop. Why? The heat, the temperature, caused the particles to go crazy, and they needed more volume. So volume is directly proportional to the temperature. That is Charles' law. Gay-Lussac's law was evident here because when I heated up the temperature, T, the pressure went up. It's doing so slowly. When you heat up the temperature, the pressure goes up. Well, I lost my temperature. That's Gay-Lussac's law. Pressure and temperature are proportional. We can talk about another type of law called Avogadro's law. What is Avogadro famous for? The number. And what does the number tell us? Atoms, molecules, ions. In other words, it talks about the individual particle. So guess what Avogadro's law talks about? Correct. Avogadro's law, which isn't up here for some reason. is V1 over N1 equals V2 over N2. You can kind of think of this one as blowing up an air mattress. You put in some air, it expands a little bit. You put in more air, it expands more. So as you increase the number of molecules, you increase the volume it takes up. These are proportional to one another. Okay. I thought this simulation might help you visibly see some of these things. And that's why I wanted to use it. Now let's get back to the rest of the information. So we said that there are 4 variables used to describe a gas. One is the pressure. Now, pressure is represented as a capital P in all its gas law equations. It has a variety of units that are possible. You can have atmospheres, which is represented by an ATM. You can have torr. You can have millimeters of mercury. If you go out and check a weather site, you might see the pressure listed as in inches of mercury. You might find it in pascals. There are a variety of units. Now, on an exam, I will give you the conversion factors for all these pressure units. So don't panic, they're going to be there. Now for volume, volume is V. Now, for the most part, we are talking about milliliters. You might be talking about liters or centimeters cubed. Those are the most common volume units. Again, there's others, but those are the most common. The amount of gas is represented with a lowercase n, and the only unit you'll be using when we talk about amount, N specifically, is going to be moles. And then the temperature is the fourth of the variables, which is represented with a capital T, and its only acceptable unit is Kelvin. You cannot talk degrees Celsius or degrees Fahrenheit with gas laws. The only acceptable unit is going to be that of Kelvin. Now, the gas law that combines all 4 properties is the ideal gas law. And the ideal gas law is PV is equal to nRT, where R is the ideal gas constant, and I like to think of R also as my dictator of units. It tells you what units your 4 variables must be in. Now, there are a variety of R's out there. You can find an R that has torr. You can find an R with millimeters of mercury. You can find an R with all sorts of things, but you're only going to get 1 R on the final exam. So we might as well get used to that one. And that is going to be 0.0821 atmosphere liters per mole Kelvin. So in other words, our R value is dictating that the pressure unit must be atmospheres. It's dictating that the volume unit must be liters. It's dictating that the amount of gas must be moles. and it's dictating that the temperature of the gas must be Kelvin. Now let's see this in action. How many moles of N2 gas are present in a 250 milliliter container at 25 degrees Celsius and at 1.2 atmospheres? Folks, when I get this type of problem, just like a lot of the other things I've done, I'll list out the information they gave me. I want to know moles. I was told that I had a volume of 250 milliliters. I was told that the temperature was at 25 degrees Celsius. And I was told that the pressure was at 1.2 atmospheres. By listing out the pieces of information I have been given, I notice that I have the 4 variables. So that tells me that the gas law I want to use is PV equals nRT, because I have all 4 variables, which means I will need the R value of 0.0821 atmosphere liters per mole Kelvin. Now, again, your R value is the dictator. Your volume, according to R, must be in liters. So you have to convert that milliliters into liters. Your temperature must be in Kelvin, according to the R. So you have to convert that temperature into Kelvin. Now that all of my units are matching up with R, I rearrange my equation to solve for the desired variable. So PV over RT is equal to N. And now I'm ready to plug and chug. So I have a pressure of 1.2 atmospheres. I have a volume of 0.250 liters. That is all divided by an R value of 0.0821 atmosphere liters per mole Kelvin times the temperature of 298.15 Kelvin. And that will give me my number of moles. And when you key this into the calculator, you get an N value of 0.012 moles of N2. You're going to see me use this process a lot, where I make a list of my variables. I identify my equation. If I have R, I make all my units match R. Then I rearrange the equation, and then I plug and chug. Let's look at another example. Trying to see what I want to use. Okay, I'll just make up one. What volume will 2.4 moles of an unknown gas take up at 37 degrees Celsius and at 720 torr? I make my list. I need to find volume. I was given the moles as 2.4 moles. I was given a temperature of 37 degrees Celsius. I was given a pressure of 720 torr. In making my list, I see I have all four variables. So that means I'm going to be using PV equals nRT. Now to use PV equals nRT, I also need the R value of 0.0821 atmosphere liters per mole Kelvin. And that R value is going to dictate the units for everybody else. So my temperature must be in Kelvin. Which comes out to be 310.15 Kelvin. My pressure must be in atmospheres. Now, to get that into atmospheres, the conversion factor is that there is 760 torr to 1 atmosphere. Or in other words, it's 0.947 atmospheres. I've made all my units match. Now I'm rearranging this equation to solve for volume. So volume is going to equal the amount of gas times R times T all over P. Plugging that into this equation, 2.4 moles times 0.0821 atmosphere liters per mole Kelvin times the temperature of 310.15 Kelvin divided by the pressure of 0.947 atmospheres will give me the volume which comes out to be, wow, 64.5 liters. Questions? Okay. So now I'm going to make you backtrack a little bit, not a lot. If I said you have 15.9 grams of oxygen and I asked you to convert that into moles of oxygen, Walk me through it. Tell me what to do. I need the grams per mole. Well, oxygen is 32.00 grams of oxygen is equal to 1 mole of oxygen. So I'll put the grams on the bottom. And I'll get roughly 0.5. Didn't mean to do that, but that's okay. Get 0.4968. We're just going to call it 0.5 moles of O2. So what you did is you took that mass and you divided it by the molar mass to get moles, correct? Now we're going to take and we're going to substitute, instead of writing out mass, I'll make it a little m. And for molar mass, I'm going to make it a double big M. And we already have a variable for moles, that's N. So in other words, the mass over the molar mass is equal to N. Now, if we go back to our PV equals nRT, and we substitute in the N we just determined, then we get PV equals our mass over our molar mass times RT. Or another way to write this is that PV equals mass RT over molar mass. Now, this equation is a very useful equation. For one thing, I could take this equation and multiply both sides through by the molar mass. And if I multiply both sides through by the molar mass, I now have the pressure times volume times the molar mass is equal to MRT. I could then divide that by PV so that I had the molar mass is equal to MRT over PV. And now what you have is you have a formula that allows you to identify of an unknown gas based on molar mass. But there's more to it. So going back to where we were, I could now divide both sides by RT. And when I do so, I get PV molar mass over RT is equal to the mass. I then can multiply both sides by 1 over the volume. And when you do so, you get PV times the molar mass, or no, excuse me, you get P times the molar mass over RT is equal to mass over volume. And where have we ever heard that term before? That, folks, is equal to the density. So in other words, you can use this variation to calculate density of a gas. So it's a very useful variation. I think we all need a couple of minutes to stand up. So let's take about 5 minutes, stand up, go to the bathroom if you need, and come back and we'll finish up. But I'm looking at faces going to sleep on me. Oh, girl, they're leaving, not coming at me. You're not supposed to get up if they're leaving. Silly goose. She just barks at people. She never bites. She just barks. I got to figure out how to break her. I'm going to have to put you on your feet because that, my friend, wasn't called. Had freedom.
sheet up here?
It's over there. Mm-hmm. Mm-hmm. I think we're all back. Feels like we're all back. Okay, so let's look at an example. An unknown gas has a mass of 3.167 grams. The gas expands to fill a 1 liter vessel at 0 degrees Celsius and 760 millimeters of mercury. What is the identity of the gas? So I was told that I had a mass of 3.167 grams. I was told that the volume was 1 liter. I was told that the temperature was 0 degrees Celsius. I was told that the pressure was 760 millimeters of mercury. Now, when I see this mass up here, that is my cue that I'm probably going to use that variation to the ideal gas law. So I will be using PV equals mass times RT over the molar mass. So the other pieces of information is the molar mass, which is what I really need to calculate if I want to know which gas I have, and R, which is 0.0821 atmosphere liters per mole Kelvin. Now, again, your R is your dictator, so your pressure needs to be in atmospheres. Well, 760 millimeters of mercury is converted into atmospheres with the fact that for every 1 atmosphere, it is 760 millimeters of mercury. So in other words, this is going to come out to be 1 atmosphere. Your volume needs to be in liters, which it is. Your temperature needs to be in Kelvin. So we're going to have to add 273.15 to that to get it into Kelvin. Rearranging this equation, which I did for you previously, it comes out as the molar mass is equal to the mass times R times T over PV. So to get my molar mass, that's going to equal 3.167 grams times R of 0.0821 atmosphere liters per mole Kelvin times a temperature of 273.15 Kelvin divided by the volume of, or the pressure, excuse me, of 1 atmosphere times 1 liter. So the molar mass, if I recall, comes out to be 70.9. Comes out to be 71. Now, considering there's probably some rounding in that mass, if you look back at the options up here of argon, let me get them pulled up. I'll give you rough shots of them real quick. That one, that one. Argon is approximately 40. Oxygen is 32. Chlorine is 70.9. HF would be 20. And water is roughly 18. You will see that the molar mass we calculated of 71 is pretty darn close to that 70.9. And so our gas would be chlorine gas. Questions? Okay, let's look at one more example. What is the density of CO2 if it has a volume, if it has a pressure of 745 millimeters of mercury and a temperature of 65 degrees Celsius. So I want to know the density of a gas. And I was given the pressure of 745 millimeters of mercury and the temperature of 65 degrees Celsius. Again, the equation to start with was that the pressure, the pressure times the volume was equal to the mass times RT over the molar mass, which, as I showed you previously, can be rearranged so that the pressure times the molar mass over RT is equal to the mass over volume, which was equal to our density. So in order to be able to do this, I've got the pressure, I've got the temperature. R is a constant of 0.0821 atmosphere liters per mole Kelvin. And my molar mass, well, I know this is CO2. So I can calculate that molar mass. That's going to be 44.01 grams per mole. Now I've got to make all my units match. So I'm going to convert that 745 millimeters of mercury into atmospheres with the fact that there is 760 millimeters of mercury for 1 atmosphere. So that comes out to be equal to 0.98. And I've got to convert that temperature into Kelvin. Which is 338.15. Now I'm ready to put all this into this equation. So 0.98 atmospheres times the molar mass of 44.01 grams per mole. Divide that by 0.0821 atmosphere liters per mole Kelvin times the temperature of 338.15 Kelvin. And that's going to give me my density. So the density of this CO2 gas comes out to be 1.55 grams per liter. Questions? Okay. So if we go back way up here, you don't have to go back that far, but when I started this, I said that we were going to gain an understanding of the gas behavior. We were going to develop some gas laws. We were going to perform some calculations with the ideal gas law. We were going to do variations where we did density and molarity. Now we're up to ideal gas laws with stoichiometry. Okay, so let's look at what I did with it. Let's look at this reaction. Let's look at the burning of octane. 2C8H18 gas. No, that would be in liquid form. Liquid plus 25O2 gas goes to make 16CO2 gas plus 18 H2O liquid. H2O gas. If 4.00 moles of gasoline are burned, what volume of oxygen is needed if the pressure is 0.953 atmospheres and the temperature is 35 degrees Celsius. Okay. When I look at this, let's talk about what I know. I know moles of C8H18. That is equal to 4.00 moles. But C8H18 is a liquid. So when I look at the rest of this, when I see pressure, that pressure has to be associated with the O2 gas. And the temperature could be associated with both. But that amount of gas has to be associated with the oxygen because it's a gas. Pressure is a gas here. We've been asked to solve the volume of our oxygen gas. Now, to be able to do that, when I look over here at the oxygen, which is what I've been asked to solve something for, I see pressure, temperature, volume. That makes me want to get my amount of gas so I can use my ideal gas law. This is where the stoichiometry comes into place. Because I know that I have 4 moles of C8H18, and for every 2 moles of C8H18, you get 25 moles of oxygen. So the amount of moles of oxygen needed for that 4 is going to be 50. That's how much oxygen is in this system. If I'm going to burn 4 moles of octane, I got to have 50 moles of oxygen. Now what I see is, yes, I get to use PV equals nRT. So I know my R is 0.0821 atmosphere liters per mole Kelvin, and I know that that is going to be the dictator. So my pressure is already in atmospheres. My temperature needs to be in Kelvin. So I'm going to add 273 to that, 273.15, and it's 308.15. And I know my moles of oxygen. So I can get my volume of oxygen. To do so, I'm going to take, and it's going to be volume is going to be equal to nRT over P. So my volume is going to equal the 50 moles times 0.0821 atmosphere liters per mole Kelvin times 308.15 Kelvin divided by 0.93953 atmospheres. And when you calculate that out, you get, 1,327 liters of oxygen. I mean, that's really not that large when you think of a gas tank, but it's a large number of liters for me. I don't usually deal with that large of a quantity. Okay, let's look at this same question again of 2C8H18 liquid plus 25 oxygen gas going to form 16 carbon dioxide gas plus 18 H2O gas. How many grams of water would be produced if 20.0 liters of oxygen were burned at a negative 10.0 degrees Celsius and at a pressure of 1.3 atmospheres. So I want to know the mass of H2O. That's what I want to know. But I was given the volume of oxygen, which was 20.0 liters. And I was told that the temperature of that oxygen was negative 10.0 degrees Celsius. And I was told that the pressure of that oxygen was 1.3 atmospheres. That right-hand side to me looks a lot like I'm going to be doing the ideal gas law with my R value of 0.0821 atmosphere liters per mole Kelvin. In order to be able to use that ideal gas constant, and in general, I need to convert my temperature into Kelvin. So now I've got PV equals nRT. This will be for the oxygen because that's what I was given information about. So solving for N, that's going to be PV over RT is equal to N for the oxygen. So my pressure was 1.3 atmospheres times my volume, which was 20.0 liters, divided by my R, which was 0.0821 atmosphere liters per mole Kelvin, times my temperature of 263.15 Kelvin. That is going to give me my number of moles. And that number of moles of oxygen comes out to be 1.2 moles. But you must always keep in mind what you were after. We were after water. So we're going to take that 1.2 moles of oxygen and we're going to convert that into the water because there was 18 moles of water formed for every 25 moles of oxygen. And the water has a mass of 18.01528 grams of water to 1 mole of water. So when you finish that, you wind up with 15.6 grams of H2O. Questions? I know lots and lots of math. Okay, so that, going back up to my original list of everything I wanted to cover, takes us to Dalton's law of partial pressures. Now, I want us to go back to the beginning of gases. We had our little simulation, and I had some red gas molecules. And those red gas molecules, they were moving in every direction, and they were applying pressure when they struck the walls, and they would bounce, go in another direction. Now, we also had the purple ones. And those purple ones were doing the same thing as the red ones. They would apply pressure where they struck the wall. And if we think about that pressure gauge that was over here, what we noticed is that when we just had the red, we had pressure, but then the purple applied its own pressure. Well, that's basically what Dalton's law of partial pressure is, folks. It says that the total pressure is going to be equal to the pressure of the first gas, plus the pressure of the second gas, plus the pressure of the third gas, and so on and so forth, depending upon how many gases we have. This statement is true only if we deal with an ideal gas and our collisions are elastic. This statement's true only if we're dealing with an ideal gas and those collisions are elastic. Now, another thing can be said though, and that is, since these are elastic, it also means that N total must equal the N of the first gas plus the N of the second gas plus the N of the third gas, and so on and so forth. Again, this only works because the collisions are elastic. In an ideal gas. Now, if we apply Dalton's law of partial pressure to our ideal gas law, you'll recall that the pressure times the volume is equal to the amount of gas times R times T. Now, for both the red and the purple gas in this case, the volume is constant. I mean, we didn't change the size of the box when we added more gas, so the volume's a constant. The temperature is also a constant. We didn't change the temperature when we added more gas. So what we can say is that the change in pressure had to be strictly due to the change in the amount of gas. So let's look at an example. A 250 milliliter sample, a 250 milliliter sample of oxygen is collected over water. This would have been something similar to what you would have done in lab if we'd have had the opportunity, if I didn't need to use today the way I'm using it. At 25 degrees Celsius and 760 torr. what is the pressure of oxygen if water vapor's pressure of 23.8 torr at 25 degrees Celsius. To help you understand what's going on, so you have your container here. This is a 250 milliliter container. Well, actually the container would be slightly more. This volume, okay, I'll get it straight here in a moment. You have 250 milliliters of gas. And that gas is sitting above water. Now, no matter what temperature, your water molecules have the ability to break loose of the liquid and go into gas phase. So you're going to have some water up here in gas phase, no matter what temperature. There's always some water in gas phase. Hence the reason we have humidity. Now, in addition to that, though, we collected oxygen above that. Now, keeping in mind Dalton's law of partial pressure, that means that the pressure total is going to equal the pressure of the water plus the pressure of the oxygen gas. So our P total minus the pressure of the oxygen gas is going to equal the pressure, minus the pressure of the water is going to equal the pressure of our oxygen gas. We were given P total as 760 torr. Minus, we were given the water vapor pressure of 23.8 torr. So when we do that subtraction, we're going to get the pressure of our oxygen. And that pressure comes out to be equal to 736.2 torr. Questions? Okay, I'm not quite done. I want to do like 1 or 2 more examples of Dalton's law of partial pressure where I add in some stoichiometry and everything. So here's the plan though. You have your test on Monday or Tuesday. The gas law portion of this afternoon is not on there, just through enthalpy. Then on Thursday, I will spend probably about 10 minutes doing some enthalpy with some stoichiometry. I will spend about 15 minutes doing some Dalton's law of partial pressure with some stoichiometry. And then I'll spend the rest of the time telling you how to study for the final. So I will finish up these discussions on Thursday of next week, but it's not going to take a lot to finish them up. So you've gotten, I would say, 99.9% of the information for your final as of right now. But I think we need to call it an afternoon. I will see all of you Tuesday, if not Monday. I'll be in my office all day Monday, so you're welcome to stop by.